This is our first video on laws of thermodynamics, and in this video we're going to look at the work in thermodynamics. And in thermodynamics, work performed by a system is actually energy transferred by the system to its surroundings. So when they ask you to, the wording in this section is really important. So when they ask you, what is the work done by the engine, means the work done on the surrounding, because when the engine does the work, then the engine does something for the surrounding. So, and when the work is done on the system, that means what was done to the engine and what was done to the gas in the engine. So work in thermodynamics is going to be just like before. In thermodynamics, work is the same as the energy transferred like before, from one system to another, like from the engine to the surrounding, from the surrounding to the engine. And the wording, how they state the problems, is going to be really important. So if we look at this picture, just as before, the work is equal to the force times the distance. And in this case, the distance is by how much the gas or liquid is compressed. So that is delta L. So the force that is applied from the pressure formula, the pressure is equal to the force over the area. So instead of the force, I can write that the force is equal to pressure times the area, delta L. But the area delta L is the volume. So the work is equal to the pressure change of the volume. And here is the tricky part in this formula. This formula has something important in it. It has a negative sign. So there is a negative sign in this formula. And what that means is when you do the work on the gas, so the surrounding does the work on the gas, the energy of the gas is going to increase because the kinetic energy of the molecules, when they are compressed, they start moving faster, the temperature increases. So the energy of the gas is going to increase. And because the energy is increasing, then the final volume is smaller than the initial volume. So you have the final volume minus initial volume. So when you say delta V, it's going to be a negative number because the final minus initial is a negative number. So in order to show that the work done on the gas is positive, you have to have that negative number because delta V is negative. So the important part to remember is how they ask the question. If they say if the gas is compressed, then delta V is going to be less than 0, then the work done on the gas needs to be positive, so you have to place that additional negative number. If the gas is expanded and the volume is increased, the work done by the gas is negative. So the work done on the gas is negative, but the work done by the gas on the surrounding is positive. So when the gas is expanding, it compresses the surrounding. So it increases the kinetic energy of the particles in the surrounding. So the work done on the gas is negative because gas is losing energy by giving that energy to the surrounding. So every time you have to solve these type of questions, you have to always remember the wording, how they ask you, does mean a lot when you have to place that positive and negative sign. And in here also, PV is equal to nRT. So you could also write that the work is equal to negative P delta V, or the work is equal to negative nR delta T. So either one of these formulas could be used to calculate the work done on the gas or by the gas. So thermodynamics is the branch of physics that deals with the relationships between heat and other forms of energy. And in particular, it describes how thermal energy is converted to a form of another form of energy and how it affects the matter. So thermal energy is the energy that the substance or system has due to its temperature, like energy of moving or vibrating molecules. So there are 4 fundamental principles of thermodynamics, were originally expressed in 3 laws. Later it was determined that a more fundamental law had been neglected, and it was called the Zeroth Law. And to form the complete set of rules, scientists decided that most fundamental law needed to be included, so the Zeroth Law. The problem, though, was that the first 3 laws have already been established, and this is why they gave the fundamental law the Zeroth Law. So the Zeroth Law states that if 2 bodies are in thermal equilibrium with some third body, then they are also in equilibrium with each other. And this establishes the temperature as a fundamental and measurable property of matter. Then the first law states that the total increase in the energy of the system is equal to the increase in internal energy plus the work done on the system. And this states that the heat is a form of energy and therefore subject to the principle of conservation. Now, if you look right here in the formula under the first law of thermodynamics, you see delta U is equal to Q plus minus W. So delta U is the internal energy of the gas. Then you have Q is the heat added or taken from the gas. And then you have plus minus the work done on the gas or by the gas. So on or by. And I'm not going to tell you whether to place the sign positive or negative until we will start doing the problems, because it depends again on the wording on and by. And the heat is the energy, so the heat is equal to C delta T, and that can be calculated or given how much energy was added or taken away. That's the energy that we covered in the previous videos. And delta U is the internal energy of the system. And we looked at this formula earlier in the heat videos, that it equals to 3/2 nR delta T when we were talking about the kinetic energy of the gas. So this was the internal energy of the gas. So it equals to 3/2 nRT, and the formula just stays forever. So if the temperature of the gas is changing, so does the internal energy of the gas, because that's the kinetic energy of the gas. So if you add heat into the system, then internal energy of the gas will increase. If you take away heat from the system, then internal energy of the gas will decrease. Then if you do work on the gas, so you compress the gas, then the internal energy of the gas will increase. If you do work by the gas on the surrounding, so the gas is expanding by doing some mechanical work, like locomotives, when they have the coal burning and steam running engines. So when the gas is expanding, it is capable of doing mechanical work. So the energy of the gas will decrease, the internal energy of the gas is going to decrease, but the outside surrounding gets some energy from the decrease of the energy of the gas. Then the second law of thermodynamics states that heat energy cannot be transferred from a body at lower temperature to a body at the higher temperature without some addition of energy added into the system. And this is why it costs money to run an air conditioner or to cool down your groceries in your refrigerator. So all laws of thermodynamics describe the relationship between thermal energy and heat and other forms of energy. And how energy affects matter. But the second law of thermodynamics is specifically about the quality of energy. It states that as energy is transferred or transformed, more and more of it is wasted. And the second law is also called sometimes the entropy law, because it states that there is a natural tendency of any isolated system to degenerate into a more disordered state. Another example of the second law of thermodynamics would be the mechanical energy, such as kinetic energy. It can be completely converted into thermal energy by friction. So you can convert kinetic energy into thermal energy, but the reverse is impossible. And to explain a little bit about the entropy, so the entropy is the loss of energy available to do work. And the second law of thermodynamics implies that the total entropy of the system either increases or remains constant. It never decreases. So entropy is a measure of disorder of the system. It is an extensive property of a thermodynamic system, which means its value changes depending on the amount of matter that is present. And some scientists predict the entropy of the universe will increase to the point where the randomness creates a system incapable of useful work. And what they mean is, right now when there are hot bodies and kinetic energy and the cold bodies, so when you have difference of temperatures, it's like almost certain things in your room. So you can sort things in your room, but over time, everything degrades. So the entropy is related to the point where no matter how you sort your room in 100 years, if nobody touches your room, it's all gonna look like broken apart. So the same is with the universe and the system, that it's an enclosed system, and eventually everything is gonna go to the point where there is gonna be not enough difference in energies to be able to do work. Like in steam engine, you have the cold and the hot. And when there is a cold and a hot in contact, then the heat is going to be transferred from cold to hot, and some mechanical work can be done. But when there is no difference between cold and hot, when there is no energy concentrated in one point compared to the other, then there's going to be no work done. So that is the death of the universe. But let's not forget about the third law of thermodynamics, which states that the entropy of the perfect crystal is zero when the temperature of the crystal is equal to absolute zero. So if entropy is the measure of the disorder in the system, and while it predicts the crystal is the definition of perfectly ordered, any positive value or temperature means that there is a motion in the crystal. So if there's a temperature, the molecules are moving. If the molecules are moving, then there is a volume because there's some kinetic energy present in the system. But if there is no motion in the crystal, no motion of the molecules, then that means it's a disorder, then there would be no volume. So for these reasons, there can be no physical system with lower entropy. So entropy always has to be a positive value. So in third law of thermodynamics, they say it's never going to be okay. It's never going to be 0 Kelvin, because you cannot have a system with 0 Kelvin. In 0 Kelvin, again, that means like in internal energy of the gas, it's D halves nRT. So if it's 0, then gas has no energy stored in it. And if there is no energy stored in the gas, so there is no gas. There's no molecules that are vibrating, because every molecule has an electron that is spinning in one or the other direction. So the quarks, they're all energy. And so if there's no energy, then it would be 0 Kelvin. So third law of thermodynamics, it says that it is not possible to reach the temperature of the absolute zero. I spent 15 minutes on the concepts of it, and you also watch the videos that I posted for you in the lessons. Let's look at some practice questions so that you might see and how to use the formulas that I just showed you. So in this question, they say in a system similar to that shown in the figure, the gas in the cylinder is at a pressure of 1/10⁵ Pascal or atmospheric pressure, and the piston has an area of 0.1 meter squared. The energy as the energy is slowly added to the gas by heat, the piston is pushed up a distance of 4 centimeters. Calculate the work done by the expanding gas on the surrounding. This is where the trick is. The work done by the gas on the system, but on the surrounding. And so assumption for the pressure remains constant. So we have the formula that says the work is equal to force times the distance, and the force is equal to pressure times the area and then the distance. So the distance vertical. So we have pressure change of the volume. So in this case, we have pressure of work is equal to, they give you the pressure, which is 1/10⁵, and they give you the area, which is 0.1, and the distance that is going to be compressed by is 4 centimeters, that's 0.04, and that will give me an answer of 400 joules. Now I have to think about the sign. When the gas is expanding, then the gas does the work on the surrounding. It loses this much energy by expanding. So it adds this much energy into the surrounding. So the sign here has to stay positive. So the use of the formula is pretty easy, and you only have to pay attention by and on and think about the positive and negative sign. But there are 4 fundamental gas processes, and these 4 types of thermodynamic processes are isobaric. When you have so in the formula you have PV, P1 V1 over T1 is equal to P2 V2 over T2. So ideal gas equation. So in the fundamental these 4 fundamental processes that have different names, when they say isobaric, they mean the pressure stays the same, like a bar pressure. So so the pressure stays the same, isobaric. Or it can be called isovolumetric. When they say isovolumetric, they mean the volume of the system stays the same whenever the processes are happening in the system, changes are happening in the system. The volume will stay the same. So isovolumetric, or sometimes it is called isochoric. Then another one is isothermal. And isothermal, in this case, you have the temperature staying the same in the system. So other quantities are changing or variables are changing, but the temperature is going to stay the same. And the last one is called adiabatic. And in adiabatic process, you have all parameters of the equation do change, but what stays the same is the heat. What that means is that no heat is added or removed from the system. So adiabatic processes can occur in thermally isolated system or under spontaneous actions as rapid expansion or compression, when the gas has no time to change its to get the thermal additional or taken away heat from the system. So for each of these formulas that you see over here, because the temperature is the same, then I can cancel the temperature from both sides of the equation. So the temperature will be canceled. So you only have P1 V1 is equal to T1. So for the next one, you have pressure is the same for isobaric. So when the pressure is the same, then you can cancel pressure in the formula. When you have volume the same, then you can cancel volume the same. and then when heat is the same, so you don't cancel any of the variables in the equation. Also, when the in isothermal system, when the temperature doesn't change, that means so delta U is equal to 3/2 nR delta T. But because the temperature doesn't change, the internal energy of the gas doesn't change. So that changes the way you look at the formula. So in this formula, you will have delta U is equal to 0. Then in this case, you have the heat is equal to the work done on the system. And in this equation, so this work is never given to you for isothermal process. So you will never see this formula given to you on formula sheets. But if they do give you the problem involved with the isothermal work done, then they will give you the formula. They will have to, because there is like no way to remember. You don't have to memorize the formula. For Adiabatic process, so your pressure stays the same, but the volume changes. So if the volume is changing, then there is work done, and the work done is delta P delta V. And I also want to point to you that work is equal to, let me see if I have this formula here. Yes, I do. So the work is equal to, right here, P delta V. So often when you have the graph, it's called PV diagrams. So when you have the graph, you have the pressure, you have the volume. Because P times V is the work, the area underneath the graph that represents the process is the work. So this will be the work done on the system, by the system. So for the next, the same, you have PV, pressure stays the same, but the volume is changing, so this will be your work, or P times delta V. And in the picture, you see that the final volume is bigger than the initial volume. So the work done on the gas is negative because the gas expanded. So you see this negative sign in the formula. Then when the volume does not change, in this case, you still use this formula. The internal energy is 3/2 nRT. The internal energy 3/2 nRT can be used for any of these processes, because that's how you determine how much energy changes. So in the next one, you have the pressure and the volume, but in this case, the volume stays the same. Because the volume stays the same, the work done on the system or by the system is 0, because there is no work that you can do on the surrounding when the volume doesn't change. So you still can have internal energy equals to 3/2 nRT, but change of the volume is equal to 0, and therefore from this formula, work is equal to P delta V. The work is equal to 0. And then for the last process, for adiabatic, your heat is equal to 0. In this case, you have this formula, because the heat is equal to 0, no heat added or taken away from the system. Then in this formula, Q goes away, and the change of the internal energy depends on the work done in the system. And so the internal energy becomes the work formula for this process, because the Q is gone and you have internal energy is equal to work, and work therefore is equal to 3/2 nRT, or 3/2 P delta V. If you compare two graphs for isothermal, you have to know what the graphs look like, because this is very common on AP exam where they ask you these kind of questions. So when you compare these graphs, you see that the work done by the adiabatic process with the same volumes and change the pressure. So you see there is work done more in isothermal process than adiabatic process. And adiabatic process is a rapid process. The pressure and the temperature changes occur at faster rate, so its curve is steeper than the isothermal curve. And the work is more done in isothermal process, because when these changes are happening, the temperature has to stay the same. So you do have to add heat into the system or take away heat from the system to be able to keep the same temperature. So there's more work needed to do isothermal processes than it is to do adiabatic processes. So in this question, they say, on all the PV diagrams shown below, the lighter curve represents the isothermal process and the process for which the temperature remains constant. But the darker curve best represents an adiabatic process, a process for which no heat enters or leaves the system. So they want you to tell which of these curves is the right one, and you see that the right one would be C, because for adiabatic process you would have less work done for the same volume, versus for isothermal process you will have more work done for the same change of the volume. So the answer is C. In this problem, they give you different temperatures, T1, T2, T3, the blue graphs, and then they say the orange graphs are different graphs. So they ask you to identify the paths A, B, C, and D in given figure as isobaric, isothermal, isovolumetric, or isochoric, and adiabatic. And for path B, Q is equal to 0. So you can see that isovolumetric is going to be A, because the volume doesn't change for A. So this is the same volume stays. The horizontal line, the horizontal axis is the volume. And then for adia, let's do this way. Isobaric is going to be D. So this has the same pressure, doesn't change, because the vertical axis is the pressure. And then between C and B, they say B path has change of the heat equals to 0. So because B has change of the heat equals to 0, and also B has less energy, less work done by changing the values. So the B is adiabatic, and C stays within the same temperature. So you see it follows the same temperature, stays within T3, so isothermal. And also in adiabatic process, temperature does change. So it went from this temperature T3 to T4. So it's on the line of T4. So the process has temperature change. So it's adiabatic as well. I didn't get the chance to do many questions in this video, but I thought it was very important for me to explain the conceptual part of the topic. You also can watch a lot of videos that I posted for you online. But there's one more thing that I want to mention in this video is quasi-static process. So in thermodynamics, a quasi-static process is a thermodynamic process that happens slowly enough for the system to remain in internal equilibrium. In other words, the process in which every state of the process is in equilibrium process. So the process is carried out so slowly that when you look at the state, you cannot see the changes. So a quasi-static process would be the flower growing. You look at it, you don't see the changes because the process is happening so slow, but you can compare the flower today and a week later and you see a big difference. I will stop our video on introduction to laws of thermodynamics at this point, and I want to thank you for watching it, and be patient with all the verbal explanation of the processes and laws of thermodynamics. I hope it helped. And in the next video, I'll do more practice questions and maybe less talking. And thank you for watching it, and I will see you in the next video.